In this video, let's talk about the relationship between position, velocity, and acceleration for an object that is moving in 2D or three-dimensional space. Now, fortunately for us, the situation in two and three-dimensional space is extremely similar to the case in one-dimensional space. In one-dimensional space, if you had a function that represented the object's position, then you could find the velocity just by taking the first derivative, and you could find the acceleration just by taking the second derivative. And the situation is extremely similar in higher dimensions. In this situation, your position function would be two-dimensional or three-dimensional. But if you wanted to find the velocity, still the only thing that you need to do is calculate the first derivative. And to find acceleration, still, the only thing that you need to do is calculate the second derivative. Now, using these principles, you can pretty much convert freely between any one of these quantities to any of the other two. For example, if somebody gave you velocity, then you could calculate position by taking an antiderivative, by going backward and integrating. Let's do a couple of examples. Suppose that an object's position is given by r of t equals 5 sine 2t, 5 cosine 2t, and 3t squared. Let's find the object's velocity and then find the object's acceleration. Well, finding velocity is as simple as finding the derivative of this vector-valued function, which we know can be done component-wise. So if I find the derivative of the x component, I get 10 cosine 2t by way of chain rule. Applying chain rule to the y component, negative 10 sine 2t. And then applying power rule to the z component, I get 6 times t. So this vector-valued function would describe the object's velocity at any given time, the direction in which it was moving, and, if we find the magnitude, how quickly the object is moving. If we want acceleration, then all we have to do is find the derivative one more time. If I find the second derivative, then using chain rule again, we get negative 20 sine of 2t. We get negative 20 cosine of 2t. And the derivative of 6t in the back just becomes 6. So this vector-valued function would capture how the object's direction and speed were changing over time. Now let's consider the reverse problem. We have an object in free fall. And when we say free fall, that means that the only force that's acting on this object is the gravitational force exerted by the Earth. If the object's initial position is given by 0, 0, 5, and its initial velocity is given by 1, 2, 0, let's try and find a vector-valued function that represents the object's position at any given time t. Now, one of the things that I know is that if I know the acceleration vector, then all I have to do is integrate acceleration, and that will give me velocity. Then I'll be able to integrate velocity, and that will give me the position function that this question is looking for. The question becomes, how, from the data that's given, can I find the acceleration that this object is subject to? Well, the key to that is given right here. The object is in free fall, acted upon only by gravitational force. We know that the gravitational force of an object acts straight downward, in this case, straight downward being the negative z direction, say, and the magnitude will be equal to negative 9.81 multiplied by the object's mass. Now, Newton's law says that that is going to be the same thing as mass times the acceleration vector. So let's go through and divide out that mass of 3 to find the acceleration vector for an object in freefall. That vector will consist of a constant vector pointing straight down with a magnitude of negative 9.81 units. And it's for this reason that this constant number, negative 9.81, this quantity called g for short, this is the reason that this g is called the acceleration due to gravity, because it shows up exactly in the acceleration vector for an object that is being acted upon by gravity only. So now that we found the acceleration vector, all that we need to do to finish this problem is to integrate that quantity twice to get the position. First, if I integrate, the integral of this 0 will become some constant in the x component, the integral of this second 0 will become some other constant, and the integral of this negative 9.81 will become negative 9.81t plus some constant in the z component. Now let's plug in the initial time and compare the initial velocity predicted by my function, cx, cy, and cz, with the initial velocity given to me in the problem, 0, 0, 5. Matching the two x's, matching the two y's, and matching the two z's tells me that c of x must be 0, c of y must be 0, and cz must be 5. So we've gotten the object's velocity. I'll replace in this expression the cx with the 0, cy with 0, and cz with the 5. Now repeating that process one more time, let's go ahead and find the position. The position being equal to the integral of this velocity vector. Now if I integrate that, the integral of this 0 will be some constant in the x component. The integral of the second 0 will be some constant in the y component. And then the integral of this polynomial in the back will become negative 0.4605 plus 5t plus some constant in the z component. Once again, let's plug in a time of 0, and let's compare what is predicted by my function with what is given to me in the problem. The initial position I was given, scrolling back up, is 1, 2, 0. So matching the x's, matching the y's, and matching the z's, and then filling those values into my r of t, I get cx 1, cy 2, and then negative 4 point, excuse me, this should have been the 9 the whole time. Whoops. Negative 4.905 t squared minus, plus 5t plus 0. That is how I would calculate the position from, in this case, the forces acting on an object with a known mass. Use the force vector to find acceleration. Integrate acceleration to find velocity. Integrate velocity to find position, and then you are done.